Mastering designing for scalability. Designers must prioritize scalability, or risk catastrophic system failure. What are the specific critical components of our system that its designers and architects need to prioritize and carefully design for scalability in order to effectively handle increased traffic, demand, and growth, while maintaining high performance, reliability, and availability? As I walked into the Guggenheim Museum in Bilbao, Spain, I was struck by the sheer scale and beauty of Frank Gehry's flowing architecture. The museum's design seemed to defy gravity, with sleek curves and soaring atriums that appeared to flex and bend in impossible ways. But what struck me most was the way the design seemed to adapt to the surrounding environment, blending seamlessly into the urban landscape. As I gazed up at the museum's undulating facade, I couldn't help but think about the parallels between Gehry's masterpiece and the challenges of designing for scalability in business. Just as the Guggenheim's design had to accommodate the unique contours of the city, so too must a scalable system be designed to accommodate the unpredictable ebbs and flows of customer demand. In my experience, there are several critical components that designers and architects need to prioritize when building a system for scalability. The first is modularity. Just as Gehry's design is comprised of individual components that can be assembled and rearranged to create a cohesive whole, a scalable system must be built from modular components that can be easily added or removed as demand dictates. Take, for example, the case of Airbnb. When the company first launched, its founders realized that they needed a system that could handle rapid growth without sacrificing performance or reliability. To achieve this, they designed a modular architecture that allowed them to add new servers and resources as demand increased. This enabled Airbnb to scale quickly and efficiently, without compromising the user experience. Another critical component is automation. Just as the Guggenheim's intricate design required advanced engineering and precision manufacturing, a scalable system must be able to automate routine tasks and processes in order to minimize manual intervention and reduce the risk of human error. For instance, consider the case of Netflix. When the company decided to expand its streaming service to new markets, it needed a system that could automatically handle the increased traffic and demand. To achieve this, Netflix developed a sophisticated automation platform that could dynamically allocate resources and adjust to changing demand patterns in real time. Finally, there is the importance of flexibility. Just as Gehry's design allows for multiple perspectives and interpretations, a scalable system must be able to adapt to changing circumstances and unexpected challenges. Take, for example, the case of Dropbox. When the company launched its file-sharing service, it quickly realized that its users were generating an enormous amount of data. To handle this growth, Dropbox developed a flexible architecture that could scale up or down as needed, without sacrificing performance or reliability. As I left the Guggenheim Museum, I couldn't help but feel a sense of awe at the beauty and complexity of Gehry's design. But I also realized that the principles of scalability that underpinned the museum's architecture were equally applicable to business. By prioritizing modularity, automation, and flexibility, designers and architects can build systems that are capable of handling rapid growth and change, while maintaining high performance, reliability, and availability. When it comes to designing for scalability, operational excellence is crucial to ensure that systems can effectively handle increased traffic, demand, and growth, while maintaining high performance, reliability, and availability. To achieve this, the designers and architects of the system need to prioritize and carefully design several critical components. First and foremost, the system's architecture must be designed to scale horizontally, which means adding more resources, such as servers, instances, or containers, as demand increases, rather than relying on vertical scaling, which involves increasing the power of individual resources. This allows the system to handle increased traffic and demand by distributing the load across multiple resources, reducing the risk of a single point of failure, and improving overall performance and availability. Another critical component is the database design. The database must be designed to handle high traffic and large amounts of data, which can be achieved by implementing a distributed database architecture, such as sharding or replication, to distribute the load across multiple nodes. Additionally, database queries must be optimized for performance, and indexing must be implemented to reduce the time it takes to retrieve data. Caching is also essential for improving performance and reducing the load on the system. By caching frequently accessed data, the system can reduce the number of requests to the database, improving response times and reducing latency. This can be achieved using caching mechanisms such as Redis or Memcached. Load balancing is another critical component that must be carefully designed to ensure that incoming traffic is distributed evenly across multiple resources, preventing any single resource from becoming overwhelmed and reducing the risk of a single point of failure. This can be achieved using load balancing algorithms such as round-robin, least connection, or IP hash. Auto-scaling is also essential for ensuring that the system can scale up or down in response to changes in demand. This can be achieved using cloud providers such as AWS or Azure, which offer auto-scaling features that allow resources to be added or removed based on demand. Monitoring and logging are also critical components that must be carefully designed to ensure that the system can be effectively monitored and debugged. This includes implementing monitoring tools such as Prometheus or New Relic, which provide real-time data on system performance and can help identify bottlenecks and issues. Logging mechanisms must also be implemented to track errors and exceptions, allowing developers to identify and debug issues quickly. In addition, queuing mechanisms, such as message queues or job queues, must be implemented to handle large volumes of requests and tasks, ensuring that the system can process requests efficiently and effectively, even during periods of high demand. Another critical component is the ability to handle failures and errors gracefully, which can be achieved by implementing fault-tolerant design patterns, such as circuit breakers, which can detect when a service is not responding and prevent further requests from being sent, reducing the risk of cascading failures. Security must also be a top priority, with designers and architects implementing security measures such as encryption, firewalls, and access controls to ensure that the system and its data are protected from unauthorized access and malicious attacks. Finally, the system must be designed to allow for easy maintenance and upgrades, with designers and architects implementing mechanisms such as rolling updates, which allow updates to be performed without downtime, and blue-green deployments, which allow new versions of the system to be deployed alongside the existing version, reducing the risk of errors and downtime. In conclusion, designing for scalability requires careful consideration of several critical components, including architecture, database design, caching, load balancing, auto-scaling, monitoring and logging, queuing mechanisms, fault tolerance, security, and maintenance and upgrades. By prioritizing and carefully designing these components, designers and architects can ensure that their systems can effectively handle increased traffic, demand, and growth, while maintaining high performance, reliability, and availability.